Okay, well, welcome, guys and girls. I just want to make sure that we're going to start on one of these lessons, Chapter 3 and 3.1, for Monday and Tuesday of next week. So I'm going to record a short video and then do a Zoom session where we can answer some questions. And I'm going to do this relatively quick, but I want to show you a couple things before we get started. Good. I hope everyone is well, and we're going to try our best to get through this and see how this goes. We want to make sure that we're trying to keep doing this every couple of days and doing this properly. So I do think everybody has knows how to find the home page. So when you log into your online site, the D2L course site, you'll see your courses along here in this window. My page looks a little bit different than yours. Make sure you're on the 1920 Semester 2 tab and find this course here, MCV4UO, MCV4UO Calculus and Vectors, Gray K. That's this course. Click on it and we'll get started. This is what the course looks like. You should know how to navigate a little bit in it. The content's going to be in here. If you want to send me an email, you can do that through the class list. And there are calendar events and activities up here. I added resources, so the University of Waterloo course courseware. The textbook is online, it's free now. The textbook solutions are here posted, and the Desmos link is here as well too. So on your home page, you'll see resources here. You'll see announcements every couple of days. I'll put announcements up. You can email me through communication and class list. Communication and class list will show everybody in the class. You can scroll down to me, I'm right here, and you can click on me to compose an email to me. The content is found under the content button, and then the variety of units and lessons we've done. Course information, student information is there if you want to review it and read it. Math tools, the Nelson textbook is also here. The math tools has a little intro on Desmos, it has a little intro on Microsoft Excel, and has a little intro on the GeoGebra, a different website, much like Desmos, that we use as well too. So we've done Unit 1, Introduction to Calculus. We've done Unit 2, Derivatives. We're going to be in pretty good shape, and I don't want people to get too stressed out about this. I want you to give it your best shot and see how it goes. I'll do everything I can to help you finish the course and teach as much of the course as we can in this time period. It might be very, very different and unique. We'll try and make the best of it as we can. So in Unit 3, we're going to start Monday and Tuesday. So I think that's Monday, April the 6th, and Tuesday, April the 7th. It's on Unit 3. Click on Unit 3, and let's go into Unit 3, Activity 1, higher order derivatives. We're going to do a short lesson on that. If you want the Smart Notebook file, it's under Unit 3 materials at the bottom of the unit, and it's this file right here. That's a PDF that I would give you in class. That's the note handout for sure. Now, if you want to do that and follow along, you can. If you don't want to, this is the lesson that you'd see, and it's basically the PDF that goes with this. So I do want to just do the intro to Unit 3 really quickly and talk about derivatives and all the applications they have. Okay, rate of change is a common application in physical sciences and science in general, and math and psychology and business. Newton developed this, and there's a little intro with it. We've got our learning goals and success criteria that are here for the chapter, and how we know if we're going to be successful, and that's it. Just on a side note, in the last week or two, I've been doing a lot of reading and research, and Newton, apparently, I didn't know this, but Newton, before we get started in Unit 3, developed a lot of calculus, and a lot of the beginnings of calculus is attributed to Newton. And from what I understand, he developed it when he was in quarantine himself during the Great Plague in Europe and in England. So Newton was quarantined for a long period of time, over 2 years on and off. I guess if my history is correct, understanding that Newton, within his quarantine period, was working on a lot of calculus applications. So whether that's a good thing or a bad thing, it might give you a little bit of energy and excitement to try and get through this. I think if Newton can develop calculus during a quarantine period, I certainly think some students can work on some calculus. Okay, higher order derivatives. Higher order derivatives are the first chapter. My online lessons follow the textbook really nicely and really carefully. So you could theoretically go and do the lessons through the textbook. You might have the textbook at home. You certainly have got access to the online textbook, and you've got these online notes. So like I said, we're in good shape maybe compared to some other teachers and classes and students here. Okay, so higher order derivatives are derivatives to the second degree, the third degree, the fourth degree, and so on and so on. We know how to express a derivative. If we have a function y equals f at x, the derivative function is expressed as such. Okay, y prime, okay, or d at f at x. Okay, here's the learning goals. I'm just going to catch up. So we see all these common notations for derivatives: y prime dy dx. The second derivative is called f double prime at x, or y double prime at x. Okay, okay, and we even see dy dx to the 2. You can take the third derivative of a function. You can take the nth derivative of a function. Usually after the third derivative, we don't talk about the fourth derivative. We talk about the nth derivative, and we evaluate f prime at 4 of x, okay, or d of 4 y with respect to d at x taken 4 times here. So just as we think we know this, okay, it's pretty easy. If I have a function and I want to find the derivative of the function, I just do it like I normally do. Okay, we did this a couple weeks ago. We should still be okay with it. You guys have done it quite a bit of time. I think I've done it correctly here. Okay, so the f prime would be negative 4x to the power 3 plus 6x minus 1. F double prime, or the second derivative, would be negative 12x squared plus 6. The third derivative, notated as f prime 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 at x, equals negative 24x. And I can go one more if I wanted to. That would be the fourth derivative. That would be negative 24. Okay, so a couple of obvious things here before we proceed with differential equations. You have to take the derivative, the first derivative, before you can take the second derivative. Before you can take the third derivative, you have to take the second derivative. And before you take the fourth derivative, you have to take the third derivative. So on and so on and so on. Okay, you have to, in order to take an nth derivative, you have to take the preceding derivative of that function. Okay, notice a couple other things too, and that's the change in degree here. Okay, if a function is degree 4, okay, or quartic, the first derivative is cubic, the second derivative is parabola or quadratic. Then we've got a linear function, that would be 1, right? And then we've got a constant. So we go from, okay, what did I say if I remember my advanced functions? The quartic, okay, or fourth degree, cubic, okay, cubic, and then, no, that's not a quartic. Yeah, it's a quartic, sorry, cubic, okay, then quadratic, linear, okay, and then constant, okay, is generally, okay, that pathway. So that might help you get some of these derivatives. Okay, so with respect to functions, first and second and third and fourth derivatives are used in things called differential equations. And differential equations are pretty heavily done in dynamic systems in engineering and in physics. So we have a function y equals x to the power of 3 plus 3x plus 1, and I want to prove or show that it satisfies y triple prime plus xy double prime minus 2y prime equals 0. So this is a proof. The first thing I need to do is find y prime. Okay, y prime would be 3x squared plus 3. And it looks like, according to my differential equation, I've got to find y prime. I've got to find y double prime. Okay, that's easily found after I find y prime. And also in my differential equation, it looks like I've got to find y triple prime. So y triple prime, okay, would be 6. Okay, so I've done my preliminary work in order to prove this. So my proof, okay, should follow a left-hand side equals right-hand side strategy here. The left-hand side is the hardest side. The left-hand side is y triple prime plus xy double prime minus 2y prime. Okay, now I substitute. I found y triple prime to be 6, and the rest of the equation is x double prime, or y double prime. Y double prime is 6x, and then minus 2, and y prime I found to be 3x squared plus 3. Okay, now I just work it out. 6 plus 6x squared minus 6x squared minus 6. It looks like if I collect like terms, 6x squared minus 6x squared, then I've got a plus 6 and a minus 6. All that equals 0, and that's what happens to be my right side. So I've proven the differential equation. Okay, so the steps involved in that is understanding I've got a function, I've got a differential equation. I start taking the derivatives, first derivative, second derivative, third derivative, for as long as what I need in my differential equation. My differential equation uses y triple prime, y double prime, and y prime. So I found those three things using my original function, and then I develop my proof. Okay. Second and third derivatives are used in displacement, velocity, acceleration. Okay, I've talked a little bit about this. You guys have done a couple of these examples. What you need to know is the average velocity, okay, is an average rate of change. It's the displacement, it's the derivative of the displacement function or the height function or whatever you want. The velocity function is represented as, okay, velocity of t, so function velocity of t at t is equal to s time at t. So that's the derivative of the displacement function equals the velocity function. Now in physics, in grade 11 physics and in grade 12 physics, you guys take this a little step further here. You find acceleration on a given interval. So the acceleration of a particle or an object in motion is used and represented with the derivative of the velocity, right? It's a change in the velocity function, or rate of change in the velocity function. So as that relates to the acceleration, it's v prime at t, and the velocity is, okay, the velocity derivative is actually the double derivative of the displacement function. So that's s double prime at t equals v prime at t, and that equals your acceleration function. So that requires, to find the acceleration, if you're given a displacement function, it requires that you'd have to take the first derivative, find the velocity, and then take the second derivative of the displacement function to find the acceleration. You can also take the first derivative of the velocity function to find the acceleration, and that's represented in this expression here. This sounds complicated. It sounds like it gets pretty complicated, but this is how it's expressed. Sometimes the displacement function is also d at t, just for distance, or h at t for height. And here's the relationship. And in summary, the acceleration function is just the derivative of the velocity function, if you like, okay, and the second derivative of the displacement function. That's all the kinds of things we need to go through and work on with respect to this. So let's try and finish this lesson relatively quickly and work through an example here, a common example. Okay, so an object is moving along a horizontal line modeling the position function given by s at t equals t squared minus 10t. It's over the interval t is between 0 and 12 seconds, where s is in meters and t is in seconds. All right, what's the initial velocity? The initial position velocity is when t equals 0. That's always, okay, when you see the word initial, that means t equals 0. Okay, so plug in t equals 0 into the displacement function and find out what's the original displacement of this particle or this position. Well, it looks like it's 0 meters. So it starts at the origin originally or initially. Okay, when is the particle at rest? Okay, so the particle is at rest when the velocity is 0. Okay, so if we have the original displacement function, okay, I think I wrote that correctly, I can find the velocity by taking the first derivative of my displacement function. Okay, for us that's easy to do. We've done these questions a lot here. Okay, so I've got t 2t minus 10 equals 0. Solve for t, okay, and that's seconds. Okay, so the velocity, or the particle, I could say, the particle is at rest at t equals 5 seconds. Okay, and that answer does fit my domain. Remember, my original domain was between 0 and 12 seconds, so that answer is good, falls in my domain. Good. So the particle stops at 5 seconds. Okay, when is the object traveling left of the origin? Okay, left of the origin, when it's traveling, okay, the word traveling is velocity, and left of the origin is when the velocity is less than 0. Okay, now I think I just found velocity, if I remember correctly. It's this function. Okay, so I have to solve this inequality. Okay, so the particle, okay, looks like it's left of the, okay, so it's traveling left of the origin when t equals, or t is less than 5 seconds. Okay, and that's for left. Okay, and for right, when is it right? Well, you probably can figure it out. It's when the velocity is greater than 0. Okay, so when the velocity is positive, it's traveling, okay, right of the origin here. So that's solving this inequality. 2t minus 10 is greater than 0. 2t is greater than 10. T is greater than 5. So t looks like, t at 5 looks like it's sort of the, I don't know, lack of turning point, I guess, if we can use that word for a function. The turning point at t equals 5, it stopped, okay, before it reached 5. So as t approached 5 from the left hand side, okay, sounds like a limit question. As t approaches 5 from the left hand side, okay, it's traveling left of the origin, and as t approaches 5 from the right hand side, okay, and t is greater than 5, that's when we have a positive, okay, a positive, okay, or the object is traveling right from the origin, or off of the origin. Okay, got it? Now, I could take this a little step further, okay, and I could take this a little step further and just incorporate my domain, okay? D, how about D? What is the initial velocity? Okay, so the initial velocity is the time, okay, when the velocity, okay, or sorry, the velocity at t equals 0 initially. Again, this word initial is always assume that t equals 0 here. So I substitute the value of t equals 0 into my function. Okay, and it looks like the object was traveling initially, okay, at a decreasing speed of negative 10 meters per second, okay, when we first started to track this. So the way I say that is, okay, so it's traveling at, okay, negative 10 meters per second initially. Okay, and the negative sign, okay, represents that speed is decreasing. Okay, acceleration. What's the acceleration? Okay, well, we have the velocity function. Okay, I think again we have the velocity function to be 2t minus 10. So the acceleration function is the first derivative of the velocity function, and that looks like it's 2. The units here are important. Acceleration units is meters per second squared, okay? So that's meters per second squared here, and that means, okay, that the particle's speed is, okay, constant, okay, it's a constant value, so constantly increasing, okay, okay, at a rate of 2 meters per second squared, okay? So between the intervals 0 to, okay, 0 to 12, I guess it's constantly, okay, increasing in speed here. These are all explained in the textbook, in the chapter of the textbook. So if you need some further information, you can check that out in the textbook. Okay, what's the total distance traveled by the particle? This is a little tricky, and again, this is why I mentioned about the textbook. So let's break our interval into, okay, 0. Okay, so left of 0, it went to t equals 5. Okay, then it stopped at 5, and then from 5 it went all the way to 12, and it went right at 12 here. Okay, so this really is kind of a, yeah, I want to say a -5, but we're really, okay, if you like that, okay, I want to maybe represent that a little differently, okay, with some numbers. Let me just get rid of that here for a second and talk a little bit about this differently. Let's find some displacements, okay? Let's show it this way here. S at 0, let's find, okay, 0 is an important mark. I think we found that earlier, the distance. Let's find the distance at 5. That was the break point. So the distance at 5 would be 5 squared minus 10 times 5. That would be 25 minus 50, okay, or minus 25. Now remember, my original displacement function, right, is t squared, okay, is it minus 10t? So this is the function I'm using. Okay, so at 5 it goes left, so that represented with the -25, and then at 5 it stops, right? And then I need a value at, okay, 12, and I'm going to put that into my displacement function. That looks to me like it's 144 minus 120, and that's 24, and that's positive 24. So now let's do that displacement line here if we like here. So here's what happens, okay? Let's go back to this original diagram that I had. So at 0, I'm going to go -25, okay, and then I stop. And then from 5, so this is at the t equals 5 second mark, and this is distance, okay, or I guess s at t if you like, distance traveled. Okay, so what happens at this point? So that's fine, we did that. So at this point I go back to and stop at 24. So 24 goes here, and that's s at t, when t is 12 now. Okay, so what's the total distance traveled? Total distance traveled, I'm going to use some absolute value bars here. Okay, so at 0, I go -25. So I got 25 units. Okay, and then I go, turn around and go backwards. So I'm already at -25. I go to 0, and then I go 24 more. So I go back to my original, or my initial starting point at 25, and then I've got another 24 to travel. I think that's 74 meters in total. Okay, I do know there's a physics way to do this. I'm pretty sure there's a physics way to do this. I'm going to leave that to the physics students in my class, and just leave it at that. You guys know more about physics than I do, and that's fine. That's no problem. I like to look at this through a math point of view. Okay, we've got one more question to do. Okay, I love these questions. These are parabola questions from grade 9 and grade 10. Okay, but we're going to do them with calculus and 4U math techniques. It'll be enough to get you guys started on some homework for the next 2 days, and certainly ask me some questions if you have any, or take a look at the textbook, or take a look at the online course here. Okay, real quick, here's the displacement function. The position function is in meters. It's a ball that's above the ground. So we probably know this, and we know that's a quadratic. It looks like it opens down. It probably hits a maximum. Okay, it probably looks like this. Okay, it looks like it has an initial amount of 1, and it probably goes up and probably drops and hits the ground like that. And this would be my height, and this would be time here. Okay, determine the maximum height of reached by the ball. Okay, so what is the maximum height reached by the ball? Okay, in the past I would just complete the square on this and find the vertex. Okay, but what happens when I at the maximum? Here's the maximum height right here. What happens at the maximum height here? The ball is climbing, it stops for a second, and then it starts to fall down, right? The gravity takes over. So the initial throw or the head of it, okay, allows it to go up, then it stops just for a second, and then it continues to hit the ground. When it stops just for that instant or just for that second, that is when the velocity is equal to 0. Okay, that's the trick here with these types of questions. That means I need to take the derivative. Well, let's call this, I'm sorry, let's call this S set. Okay, so I want to find when velocity equals 0, and I want to find S prime at t, and I know that's my velocity. Okay, so what is S prime at t? It looks like it's negative 10t plus 30. Derivative correct? Check it before you jump into it. And I want to set this equal to 0. I'm pretty sure it's correct. Okay, so now what? Solve for t. Sorry, you guys might be able to hear AC/DC in the background. Okay, so at t equals 3 seconds is when the ball hits the maximum height. Okay, now I might at times want to find out what that maximum height is. I can do that really easily. I just put it back into my original formula. Okay, okay, can I do this math correct? Okay, 9 times negative 5 is negative 45 plus 90 plus 1. Okay, that's 46 meters. I hope I did that correctly. Yeah, I think so. All right, 46 meters is the maximum height of the ball. Okay, determine the velocity of the ball when, okay, it is 1 meter above the ground. Okay, so what's the velocity of the ball? Determine the velocity of the ball when it is 1 meter above the ground. Okay, so I need to find the time when it's 1 meter above the ground. Okay, so the time, okay, so I need to find my t squared plus 30t plus 1 equals 1. Okay, it looks like I can solve that quadratic without using the quadratic formula. Okay, so just get rid of my 1's. Looks like I can factor out a negative 5t. That would leave me with t and a minus 6, I think, correctly. Just double check. Yep, good. Okay, so therefore negative 5t equals 0, or t minus 6 equals 0. So t equals 0 and t equals 6. Okay, so 2 answers. Well, that makes some sense. Okay, think about it. Okay, remember when I graphed that originally, that initial height is 1. Okay, it's where the ball started. So it's 1 meter. It's 1 meter above the ground when t equals 0, and it's 1 meter above the ground. Okay, when t equals 6. What's the velocity when it's caught 1 meter above the ground? I'm assuming that's at the tail. That's at the tail end of. Right. Okay. When it's caught, it's probably down here. Okay, so that would be when t equals 6, and I want to find the velocity at 6. Okay, so what is my velocity function? I forget it here. Negative 10t plus 30. So negative 10t plus 30. Negative 60 plus 30, okay, is negative 30 meters per second. Okay, so the velocity, it's decreasing right? It's coming down, so it's decreasing. The velocity is negative. Okay, the velocity is, okay, negative 30 meters per second when the ball is tossed. Okay, so work through some of these examples. Take a look at the textbook questions. Take a look at the online lessons. They're explained in there, and I walked through this as well too here. So you should be able to do some of these homework questions, and you've got Monday and Tuesday to work on them. Thanks and good luck. Feel free to send me an email and work through these questions when you can. Thanks. Bye-bye.